density is the volume charge density that comes from free charge. Charge is free to move. This bound charge that I'm talking about is not really a charge per se, but it arises from the polarization. Then in here somewhere.
Yeah, it's on the.
So then I can put this on the other side. I can write del dot E plus P, right, to be equal to rule 3. And so before I write the del dot D equation, what I have to write is that I define then a displacement vector, in this case for mass wells, which is E plus P. And so I can write my equation as del dot D being equal to rho 3. And the other equation, of course, is that for electrostatics anyway, that the curl of E is equal to 0. So now my equations get involved like this, in which now D is equal to this. Okay? Now, there might not be a relationship, a direct one, between E and P. P could be in an electric. As you will see, it's so permanent polarization that you are given. And therefore, what is the relationship between E and P? You have to keep that in mind. If there isn't one, like in the case of electrics, there isn't one, like a magnetization in the case of a permanent magnet, right? You don't induce anything. This thing already has a P. So now there is no relationship. And so now I have to derive the electric field from this P, okay? Then it comes a part in which the P is induced. So there are two cases in which P is not induced, it's permanent, right? And so you cannot establish any kind of relationship between E and P. E arises because of this P. And so D is always defined this way. So this is always true, this is always true. So here comes some approximation that we have to make. And so these equations are correct. Here 1 and 2 are Maxwell's equations for everything, right? So now where are the approximations that we have to make is this one, in which now you induce a P because of the presence of an electric field. If I don't have an electric field, I don't have a P, right? So this case, then, what I'm saying here is it's linearly proportional, the P is linearly proportional with E. It doesn't cause E squared, okay? And that is then a linear dielectric, okay? If chi here does not depend on position, you know, where the material is all the same stuff, say oil, or that stuff that they put on PCPs or they put on the big transformers, right? Then you have no matter where you look at it, you have the same polarization. Then if it's independent of position, then this will be a homogeneous, linear and homogeneous. We're always going to treat cases that are linear, right? Because we don't want E squared in here, so those are what we get into what we call nonlinear optics, or nonlinear response. But as long as it's linear, this chi could depend on position. And we'll do a couple of problems in which you know what the polarization of the chi depends on position, okay? So, but if it's in this form, I haven't specified whether or not chi is homogeneous or not, they can immediately write D, which is E plus P as epsilon 0, 1 plus chi times E, right? Immediately write that. So then I can define then my chi, which is now what I call the electric susceptibility, and it's a very important quantity. If you know that quantity, you know everything of the dielectric. Then you can write it in this form in terms of this kappa, which is the relative permittivity. And so if I'm interested in the absolute one, so the relative one is called relative because it's relative to vacuum, which is the epsilon 0. So kappa is really the absolute value divided by epsilon 0. Then I can write it in this form, okay? So now what happens to this equation, right? So this equation now you have made a relationship, and these are now for cases that involve a induced polarization. We're going to do a couple of examples at the beginning in which we don't have anything induced. P is there. But if it's induced meaning that you get a P because of the presence of an electric field, then this whole thing applies to that case. And now I'm getting with this equation, del dot D, right? So now what happens? Let's substitute for this equation what it is in terms of epsilon. So I get that del dot epsilon E is equal to rho 3. And here is where it comes a part where epsilon if it does not depend on position. It's a homogeneous thing. I can take it out of this thing, right? And then I can say epsilon del dot E is equal to rho free, right? If, right, epsilon is a constant. If it's not a constant, you cannot do that. It stays inside. As a matter of fact, it gives rises to the bound charge. But you yourselves can derive now a relationship between the bound charge that I have, rho bound, and this rho free. You see, you can do that because epsilon, you can pull it out, and this del dot E should be equal to rho total, which is rho free plus rho bound. Yeah?
Can you just remind me the difference between rho bound and rho free? It's like...
Okay, so when you talk about rho free, that's the only rho that we talked about always. This is electric charges, right? This is the thing that gives rise to electric fields and move along. The bound charge is not really a charge per se. We don't talk in terms of you having a different type of charge. It comes from the fact that you have a polarization field, right? And you can relate then the divergence of that field with a quantity that is a scalar that we call the bound charge, just so that it's consistent with Gauss law and all that we come up with the next time, right? So what gives rise to this rho bound is the polarization vector P, right? And you have to make the decision at this level. Usually when you have an electric charge, you know that that gives rise to an electric field. And so the charges are the what? The sources of the electric field, right? If I don't have any charges, I don't have any electric field. That is what we have learned. By their footing, you cannot treat the bound charge like giving rise to a polarization vector. There is no such thing. I have a polarization vector P first, and the bound charges and the surface bound charge is an artifact of how we present this. Okay? Is that clear? So we have to use this rho bound equal to minus del dot P and sigma bound E dot N because we treat the formalism in the same way as before. This is how we write it. So I can make this. See, I don't have to do these dot products. I don't have to do that. I can express it in terms of this. Okay? But it's due to the polarization. So now what? Now we go into this regime in which I have a linear isotropic dielectric. Okay? Homogeneous. I should have included that in there. Homogeneous meaning it doesn't depend on the potential, but it's a linear and isotropic. Isotropic means that no matter where you look, you have the same response of P. Okay? Which amounts to having my chi being not a tensor. So when I look at P, this is basically equal to epsilon 0, remember, chi times E, right? This chi that I have here is not a tensor, but if you had something that depends on orientation, then you will have to have this sort of thing. So then the component of polarization in the alpha direction depends on what the electric field is in the beta direction, right? So that is clearly not isotropic. So in different directions, you get different polarizations. And that is clearly not the case we're going to treat here. So then these are the equations that I have. E is minus del D that I have, and then I have the del dot epsilon E is equal to rho free, right? Now, let's assume that it's linear isotropic, right? And homogeneous. So if it's homogeneous, then I can put this out of this, right? Put this underlined here. This is very important. So then I can pull it out, and so then I get the epsilon del dot E is just rho free. And so now, since E is just minus the gradient of the potential, and then I can write that the Laplacian now, the Poisson's equation is just this old Laplacian. I mean, the old Poisson equation, but instead of epsilon 0 here, I just put an epsilon. That's all.
What is D, Professor?
D?
Yeah.
The displacement.
Okay, thank you very much.
So now, what are my boundary conditions? Because these are the equations that I have now. These are the equations, right? These are the equations that I have now. I have to apply boundary conditions on these equations. And so what are those equations? The first one, of course, is you apply Gauss law to this thing, right? This is what usually we do, right? And so imagine that now I have an interface, and this unfortunately doesn't look right. This is an epsilon 2 in here, and this is an epsilon 1 in here. So you have different materials that have different permittivities. This could be some material like plexiglass. This could be air. Air doesn't have epsilon 0. Epsilon 0 is for vacuum. Air actually has a permittivity that is non-zero. Right? So, but it's not big. So we usually treat cases in terms of the relative permittivity, right? In these epsilon zeros, because remember the units of epsilon 0, 1 over 4 pi epsilon 0 is 9 times 10 to the 9 Newton meters per square. We don't use that, we use kappa. Because kappa, you can say, is 1,000. It's 5. It's a dimensionless, right? So if it's 1, kappa is 1, that is relative to vacuum, so it's vacuum. If it's 2, it's something that has twice the permittivity of vacuum, right? And so on. So that's what we do kappa more than anything. So this is the absolute value. So here, if I do this, I have to say that then the difference between D2 and D1 is sigma free, which means that if I don't have any surface charge density, and when I talk about surface charge density or volume charge density, and I don't use the word bound, I mean that it's the free stuff. That's the usual way that I treat it. So if there is nothing here built up on this interface, it's no charge, in other words, then the displacement field is continuous. And the tangential component of E is always continuous. Okay?
Yes.
So now, what do we get if you have a linear isotropic homogeneous dielectric in which now epsilon, right, E is equal to D, then this condition, D2 minus D1 equal to sigma free, right? Then in the absence of a friction surface, so sigma F is equal to 0, what I get is that epsilon 2 E2 normal is equal to epsilon 1 E1 normal. So the normal component of the electric field no longer is continuous, like remember when we're taking the derivative with the potential, that is electric field. Now, no longer that is continuous if you have two different permittivities. Say this is plexiglass, this is air, right? Or this is the water in a pool, and this is the air outside the pool. There is now different epsilons on both sides, and therefore the normal component of electric field will never be continuous because these epsilons here and these epsilons are different. So there is no way that this guy is going to be equal to this guy. The product of epsilon 2 times C2 will have to be equal to this one, right? So say that this epsilon 2 is greater than this one. The water has a bigger permittivity than air, right? But this is air. So that basically means that then the normal component of the electric field inside the pool for light, say, have to be smaller than what it is outside. So that's what we mean by the bending of the light, right? The light comes in at some angle, and then when it hits the pool, this normal component to the pool, in the other one is smaller. So that if it's smaller, that means that this thing is tilted, because the normal component is it's a projection of that vector onto the normal direction, right? And if it's smaller, it means that it tilts more. So until, if it's 0, basically it's tangential to the interface, right? So that is the case that always happens. So now let's do some problems. And so for these, you have to write a little table yourselves, and I like to try to do this before you do this. All of this stuff that I put in here, you should have it on the table. You should know what D is, E plus P is that. You should know what basically the relationship between P and E is, which is this chi if this is induced, okay? And then of course you have to write this. This is what I have. So you keep that in a safe place every time you look at one of these problems, because we're going to do the problems we've done before. But in this case, they are going to be treated with these new boundary conditions. So this doesn't show very well, but this indicates a vector that it is all in the P direction, in the Z direction, right? So you have a sphere of radius A, and it has a constant polarization P, which is P0K. Find the electric potential and the electric field inside and outside the sphere. So this is the first one. Let me see if we can actually go ahead and see what we're going to do on the second one. Is similar to this one, but now this has an epsilon. It's not a p that it has. The other one they gave you p is in the z direction. This one has an epsilon inside that it is, say, this will be plexiglass. So you have a plexiglass sphere, and you have air on the outside. In this case, we're going to treat it as vacuum on the outside. And you impose an electric field on this, and now we have to find the potential E inside and outside. So we have done this problem before, right? It's a rounded sphere, for instance, right? Now, this is a little slightly different, so the math should not be the same. So I'm not going to do these things on the blackboard on the thing. I'd rather do them on the board. So let's do this one first. So how would you do this one? So this one, it basically says that you have a sphere of some radius A. And this is the z direction. And now this has some polarization vector, which is constant inside. So now P is equal to P0 in the k hat direction. That's all. So how would you do this problem? I don't want to take too much time, and I want to do at least 3 problems. Let's write what B is. Say B, what would be induced? One over 4 pi x equals 0, right? You have this. I don't know if we put this slice on top. I can't show this, but let me see if we will show it. So we have this expression, right? P dot n and the divergence of P, okay? It gives me sigma bound and rho bound, okay? So this will be the potential evaluated at some location, okay, which I'm going to, if I put it over here, so this is my observation point at R, and this is theta, right? Then you can say, well, the potential at R and theta then should be equal to the integral of my sigma bound dA prime over the integral of R minus R prime. But since this is on the area of my, we call it, this is the, on the area, the surface of the sphere, then my vector R prime will have to be, for this term, will be on the surface of the sphere, so it's A in the R hat direction. So this is R minus A in the R hat direction, right? Plus, and this is over the surface, plus, of course, I have the one that has to involve rho bound E prime, and this is now not on the surface. Okay? So this is one approach that I have. And so, this is one approach to follow. And the question is, do we use that? What is rho bound and what is sigma bound? Now, if you have a rho bound, you can show, remember what rho bound was? I didn't write it here. This is the only thing that one has to remember in my things. This rho bound, remember, was equal to minus del of P. Sigma bound was equal to P divided into N. Remember that?
So it's voltage in interior, and that, and the V equals,
Where, here?
yes, the very little writing on V, on voltage.
Well, it's symmetric.
Interior?
This is induced.
Oh, induced. Thank you.
Okay, so I have this expression, right? So So I have this expression that I have here. And now
Thank you.
what is, if from this expression, rho bound, I didn't mean S here, this is rho bound, right? You can show that the bound charge, Q bound, right, is equal to zero, always. Q bound would be the total bound charge, which is basically the integral of this rho bound over the entire volume. And then, of course, you have to use Gauss law for that, right? The divergent. And so that will have to be zero. Okay, so there are problems where you end up with some rho bound inside and a sigma bound. And you can show them when you go to the outside of that, the sigma bound exactly cancels the rho bound over the volume. So the amount of charge that you have on the volume is exactly equal to minus the amount of surface charge that you have on this thing, because the Q bound is always zero. Okay, remember that. So now I have this. So what is rho bound? P is equal to P0 in the K hat direction. What is the divergence of P? Zero. What is sigma? That should be equal to P0 K hat, plotted into the normal, which is the R hat direction, right? So then this should be equal then to P0 cosine of theta, right? So then my potential then reduces to doing the integral V loose of R and theta now is equal to 1 over 4 pi epsilon 0. Now I'm going to put a P0 in here because I'm going to take that out of the integral of the cosine of theta. Now I have to do the integral of a squared d of omega, right, which is this dA prime, divided by, now I have to have here r squared minus 2ra cosine of theta plus a squared to the 1/2. And this then is on the z-axis. Why did I do that? Because you have here r and you have a in the r hat direction, right? So this term, you are not looking in the same r here. So there is an angle that you have to look between wherever you look on the sphere here. Okay. So if I place now my r hat that I have here on the z-axis, so I have minus a k hat here, then I get to that. And now I have to do this integral. So now, I'm going to just write some of the terms, and it's a good practice for you guys to do this. So what do we get? We get that this can be written as d0 a quantity squared times 2 pi. So this is going to be 2 epsilon 0, because the 2 pi of d omega prime times the integral now from -1 to 1 of u du divided by, now I'm moving in the z-axis, remember that. So then this is equal to z squared minus 2zau plus a squared. If I'm looking in the z-axis, this has to be in the z direction. And what is u? U is just the cosine of theta. Right, so I have changed variables. So now I have to do this integral, right? And so I have to define another quantity, S, to be equal to 2z a u. And now c squared plus a squared, I'm going to call this lambda. axis, then would have to be equal to V0 A squared over 2 epsilon 0. I'll turn around in a second. So 4z squared times the integral from minus 2ZA plus 2ZA of S squared ds divided by the square root of this lambda minus. So when we do this integral, and you know, you can do this integral on your own, then what you end up is with a condition of simplify this so I don't write too much. So you have to do this integral, and you're going to end up with a condition again of the form of minus the magnitude of z minus a minus z times a minus the magnitude of z plus a plus z minus a. Okay. I have to go a little closer to this. And the reason we get this c minus a, you can do this, is because you get the square root of c squared minus 2az plus c plus a squared, right? So what is the magnitude of z minus a? For me, this is the square root of z squared minus 2za plus a squared. That has to be always, no matter what I have, is the magnitude of z minus a, right? And the magnitude of z plus a is equal to the square root of z squared plus 2za plus a squared. Why? Because z can be negative. Right? This is what. This is what you end up with. So what we simplify using this condition for what happens when z is greater than a and z is less than a and stuff like that, what I get is this. So outside the sphere, the magnitude of z minus a is equal to z minus a. Magnitude of z plus a is equal to z plus a on z greater than 0 axis, right? So I can write then the phi outside as a function of z is equal to p0 a cubed over 3 epsilon 0 z squared. And the electric field that goes with this, E outside, in the z direction, the function of z, then is equal to minus dv dz. So this is equal to 2 p0 a cubed over 3 epsilon 0 z cubed. This is the outside field. So it goes as 1 over z squared. The inside get that the, let me go to it here. Inside we get that the magnitude of z minus a is equal to a minus z, and z plus a is equal to z plus a on the z greater than 0 axis. So then v out, is equal to bz divided by 3 epsilon 0. And E in the z direction in minus 1/3 B0 over epsilon 0. And this is an important result, the last one, minus 1/3 B0. So it's in the opposite direction. And that is the value that it has, okay? So now I ask you, what is the field at anywhere as a function of r and theta? I did it on the z-axis, but I want to find it on any r and theta. What do I have to do? The Legendre polynomials, and I have to multiply by the appropriate power of the Legendre polynomial, right? So in this case, if this was a z, right, there's just one power. It's r cosine theta, right? So then outside, off axis, then b in, right, on r theta is then equal to b0 over 3 epsilon 0 of r cosine theta. Because I substitute for, this is the only term that I have, is a linear term. I don't have any other power terms. Remember, each power term, what I do is I change the z to an r, and then I multiply by the appropriate p1. In this case, it's if I have a power of 1, I have p1. If I have a power of 2, I will have p2, and so on. So what about this one? I have 1 over c squared. This is a p1 or a p2. Remember, it went as 1 over r to the 2l plus 1, right? At the bottom. So then in this case, you still have the L equals to 1 term, right? So then B out of R theta now is equal to B0 A cubed divided by 3 epsilon 0 R squared times the cosine of theta. And now notice one thing. What happens now if I set B out at A and theta has to be equal to B in at A and theta? Right? And it is, because this is A cubed over A squared is B0A over 3 epsilon 0 cosine theta. This will be P0A 3 epsilon 0 cosine theta. So they are exactly the same. They have to be, right? If you don't do this check, then something will go wrong. So then this is what it is. And now that I have the potential anywhere, now I can calculate the theta value of the electric field and the R value of the electric field. I did it for the Z direction, but now E, right, vector, right, should be equal to minus del of Z vector. So ER should be equal to minus dV dr, and E theta should be equal to minus 1 over R dV. So we did this problem using, you see now all the problems that we will do, we use basically the plethora of techniques that we have used for different problems. And so here we use the integral expression that we have for what a polarization vector P is. And now notice that I got an E out of this. right? So I get what the E field is, inside and outside. And inside is constant. Inside is constant. Now you might say, well, wait a second. What about this expression here? Well, you will get it to be Z, right? When you take this derivative, right, you will see that the field is basically because of the cosine theta, so the field really is in the Z direction inside, right? So the field inside should reduce to, if I use this expression, so E in, right, as a function of R and theta should be equal to that expression that I have here, minus 1/3 of P0 over epsilon 0 in the k hat direction. That's what it's supposed to be as a vector. And you see that k hat is what? This, if I express it in terms of R and theta, is cosine theta, right? And I have a term in the R hat, and I have a term in the theta hat. But the vector itself is k hat. So you can go back to that page 42, problem 227, and there you have k hat in terms of R and theta hat. Okay? And you will find that that's exactly what it is. So it is constant. Okay. Questions with this?
So what we're doing here,